Welcome to NMR video part 3. Protons in a molecule that are of the same type, that is, primary, secondary, tertiary, that are in structurally similar environments, tend to have similar chemical shift, that is, delta values. These values are conveniently available in tables. You'll find such tables in the packet on NMR that's posted on Moodle. There's also a table in your textbook, and of course you can find such tables in various websites on the net. Let's look at the tables in your packet. Begin with table 10.2. Table 10.2 lists average chemical shifts of aliphatic protons. These include methyl protons, methylene protons, and methine protons. The next table, table 10.4, gives chemical shifts of protons on unsaturated carbon. Unsaturated carbon groups include a hydrogen bonded to a CC double bond, a proton attached to the carbonyl carbon of a carbonyl group, proton bonded to a CC triple bond, and a proton attached to an aromatic ring. Here, the entry in the table, we use the symbol AR that stands for aromatic. Most times, this will be a proton attached to a benzene ring, but it also could be other aromatic rings. The next table, table 10.5, gives chemical shifts of protons bonded to hetero atom elements, namely oxygen, nitrogen, and sulfur. Let's go back to table 10.2 and look at some details. First, we'll look at methyl protons. Methyl attached to a hydrocarbon has delta values that fall in the range 0.8 to 1.2. Methyl attached to a CC double bond, 1.6, 1.9. Notice the values here are a little bit higher delta than here. That's because a CC double bond has an electron withdrawing effect, lowering the electron density about the methyl hydrogens, increasing the chemical shift value. Methyl attached to a aromatic ring has a chemical shift that's a little higher, 2.2 to 2.5. That's because of the electron withdrawing effect of the benzene, the aromatic ring. Methyl that's attached to a carbonyl group is 2.1 to 2.4. That's because of the electron withdrawing effect of a carbonyl. A methyl attached to a nitrogen falls in the range 2.2 to 2.6. That's because of the highly electronegative character of the nitrogen withdrawing electrons from the methyl hydrogens. The next entries, we see a methyl attached to an oxygen. When the methyl is attached directly to an oxygen, notice here the delta value is even higher than the values we looked at before, 3.7 to 4.0. That's because the oxygen strongly pulls electrons away from the methyl hydrogens. This is an abbreviation for a ester group. Methyl is directly attached to an oxygen, and the electron withdrawing effect of that ester group gives an average delta of 3.6 to 4. Here, a methyl attached to an oxygen attached to an aliphatic group, 3.2 to 3.5. The next entries are important because the electron withdrawing group in each case is a carbon-oxygen group. But what's different in these entries is that the methyl as we move down the list, is further and further away from the electron withdrawing oxygen. So when the methyl is directly attached to an oxygen, you can see a fairly high delta value, 3.2 to 3.5. When there is an intervening methylene group here, where the methyl is further away from the oxygen, then the delta value is not as high, 1.2 to 1.4. The inductive electron withdrawing effect of the oxygen decreases. It falls off as it gets further away from our methyl protons. The next entry, the oxygen is even further away, and the resulting chemical shift is a bit lower, 0.9 to 1.1. Let's look at some methylene protons. Methylene in a hydrocarbon is 1 to 1.5, chemical shift range 1 to 1.5. Now let's actually compare that now with the methine protons. The methine, single hydrogen in a hydrocarbon, 1.4 to 2. Well, compare the delta values for methyl, 0.8, 1.2, about an average of 1 delta. Methylene, 1 to 1.5, an average of 1.25. And a methine, 1.4 to 2.0, an average of about 1.7. And what we're seeing here is a general effect I'd like to comment on. The average chemical shift of aliphatic protons follows this trend. Methyl hydrogens tend to be at the lowest delta value, lower than methylene, and methylenes are of a lower delta value than methine hydrogens. And that trend is generally followed. The reason for that is a bit technical. Let's look at some more methylene proton values. All right. You have a methylene attached to an aromatic ring, 2.5 to 2.9. Notice the delta value here is a little larger than a methylene in a hydrocarbon. And again, that's because of the inductive electron withdrawing effect of the aromatic ring on the methylene hydrogens. Methylene attached to a carbonyl group, 2.3 to 2.7. It's due to the electron withdrawing effect of the carbonyl group. A methylene attached directly to an oxygen, notice 3.4 to 3.8. It's even a higher value, higher delta value than we saw previously. And that's because the oxygen is a more strongly electron withdrawing group compared to carbonyl group or aromatic ring. Here's a methylene attached to an oxygen of an ester group and fairly high delta value, 3.7 to 4.1. A methylene attached to a nitrogen, 2.5 to 2.8. Methylene attached to a halogen, notice that's a fairly high delta value because of the strong electron withdrawing effect of halogens. When you have a methylene on two chlorines, look at how high the delta value is. So two chlorines directly attached to the carbonyl group have a very large electron withdrawing effect, increasing the delta, the chemical shift, to 5.3. Now let's look at some methine protons. Methine attached to an aromatic ring. There's a deshielding effect because of the electron withdrawing effect of the aromatic ring. Have an average of about 3 compared to an average of 1.9 7 in a hydrocarbon. A methine that's attached to a oxygen here of an alcohol. The oxygen, because of its high electron withdrawing capability, gives us a fairly high delta value, 3.5 to 4.0. And then here, the methine that's attached to 3 chlorines, this is the compound chloroform, with 3 electron withdrawing chlorines directly attached to the carbon bearing the methane hydrogen. 7.27, very high delta value, highly de-shielded. Here are some miscellaneous entries for methyl groups. In each of these cases, methyl is attached to a fairly strong electron withdrawing group, giving chemical shifts that relatively high in value. All right, let's look at alkene protons. Protons attached to a CC double bond. You can see here that the delta value compared with previously seen values is fairly high, an average of 5 or so. That's a higher delta than we'd seen for the aliphatic protons in the previously listed table. And the effect of that is a bit complicated to explain, and I will actually do that in part 4 video. But for right now, it's not an inductive electron drawing effect that's creating this high chemical shift, but it's due to the location of the proton in the magnetic field that's generated by the circulating pi electrons of the double bond. And again, we'll have more to say about that later. When you have an aromatic proton, a hydrogen attached to an aromatic ring, notice dramatically the delta range 6 to 9. It's a very high delta value. There's an enormous de-shielding of the proton attached to an aromatic ring. This is not because of an inductive electron withdrawing effect. It has to do with the location of the aromatic hydrogen in the magnetic field that's created by the circulating pi electrons of the aromatic ring, and we'll have more to say about that in an upcoming video. Interestingly, the acetylenic proton here, when the hydrogen's bonded to a CC triple bond, the delta value is fairly low. In other words, it's fairly shielded compared with values we'd seen for an alkene proton, for instance. And that is due to the location of the acetylenic hydrogen relative to the magnetic field generated by the circulating pi electrons of the carbon-carbon triple bond. And again, that's something we'll go into some detail on in the upcoming video. Hydrogen that's attached to a carbonyl carbon, notice how high the delta value is. It's highly de-shielded, and the reason for that will also be explained later. Table 10.5, examining some of the entries here. Here there's a considerable variation. A hydrogen attached directly to an oxygen, as in an alcohol or phenol. Well, for alcohol 3 to 6, for phenol 6 to 8. The chemical shifts tend to be higher because of the electron withdrawing effect of the oxygen. But there is a considerable range here, fairly wide range. Look at the third entry though. This is a carboxylic acid proton. Look at how high the delta value is. There is a considerable de-shielding effect for that type of proton, 10 to 12. This hydrogen is a hydrogen of an enolic type group, and this is a very high delta value. This is extremely de-shielded. This is about as de-shielded as you'll ever find for a proton in any organic molecule. Nitrogen-bound protons, take a look at that on this part of the table. There's also considerable variation that we see for an amino proton 0 to 2.5. An aromatic ring was attached to the amino group. The delta value is a little higher, 3 to 4.5. The amino group attached to a carbonyl group of an amide, 5.5 to 7.5. Okay, here we have this Nmr spectrum of ethyl phenyl acetate. The spectrum is taken with a 60 megahertz spectrometer. Our task is to interpret this Nmr spectrum. That is to say, which sets of protons in the molecule correspond to which of the Nmr signals. Now there's a number of things that we can do in that regard. What I like to do when I'm interpreting an Nmr spectrum is first count the total number of sets of equivalent hydrogens. This is important. The number of sets of equivalent hydrogens equals the number of basic Nmr signals in the spectrum, apart from splitting that might occur. So, how many sets of equivalent hydrogens are there in this molecule? All right, we have the methyl, that's one set. There aren't any other methyls equivalent to that. We have this methylene, that's the second one. Now we have another methylene, but that's in a completely different environment. So this methylene is the second set, this methylene is the third. And now we come to the ring hydrogens, the benzene ring hydrogens. Now technically, the hydrogens on the ring are not equivalent because you have ortho, meta, para. They're not the same. However, when you have an alkyl group attached to the benzene ring, they're very, very close. We say they are approximately equivalent. You can see the difference between them if you use a higher field instrument, something higher than 60 megahertz, like a 300 or 400 megahertz instrument. But using this lower field instrument, then these benzene ring hydrogens are not going to be that different. So we'll regard all these ring hydrogens as approximately equivalent and regard all of them as a single set of 5 equivalent or approximately equivalent protons. So our total count would be 1, 2, 3, and 4 sets of equivalent hydrogens. We should see 4 basic Nmr signals in the spectrum. Here's 1. Remember, we don't factor in the splitting. 1, 2, 3, 4. Now, which signal corresponds to which set of hydrogens, though? We're going to use 2 things to help us determine this. We'll use chemical shift values from the table, and we'll also use the splitting information. First, we look at the ring hydrogens. If you go back and look at the table, the chemical shifts of protons on unsaturated carbon, this entry here, we expect a benzene ring hydrogen to have a chemical shift between 6 and 9 ppm. you'll note that we have this signal here. It's about 7.2, and that falls in that range. Therefore, we can assign this signal as caused by the phenyl ring hydrogens. Alright, let's look at this methyl. What would the chemical shift be for that? Well, again, we use our tables. Alright, what we want is a methyl connected to a methylene connected to an ester oxygen. Unfortunately, that precise entry is not here, but we do have this entry, which is fairly close to our molecule. We have a CH3 attached to CH2, an ether oxygen, not an ester oxygen. And in this particular case, the methyl is far enough away from the oxygen that it's okay to use the value here to make an estimate. And that estimate is, well, the average of 1.2 to 1.4 be 1.3. So we're going to estimate the chemical shift of the methyl, of that methyl in our molecule, to be 1.3. We'll go back now. So 1.3, and we have this signal, again, apart from the splitting. It's about 1, so it's a little bit off, and again, what we're making here are estimates, so we don't expect exact agreement. So just based on chemical shift, I'm going to say that this signal is due to this methyl. All right, now we come to this methylene. We want a methylene attached to an ester oxygen. Let's go back to our tables. All right. Now, methylene attached to an ester oxygen. Here it is right here. There's a methylene attached to an ester oxygen. It tells us the chemical shift for that falls in the range 3.7 to 4.1, and we'll guesstimate about 3.9. And we'll go back to our molecule now, 3.9. Well, we have two signals that are fairly close together. Since we're making estimates, you don't want to take that 3.9 too literally, and the best we can now say is that with our estimate of the chemical shift of 3.9, it could be either this signal or that signal. Well, let's go on. Right, the remaining methylene. Now this one's going to be a little bit harder to estimate the chemical shift because it's attached to two substituents, two electron withdrawing substituents. If we go to the tables, we won't see a precise entry, an entry that is precisely that situation. So we're going to try to make some estimates, and here's what we'll do. Our molecule has two substituents, benzene ring and an ester carbonyl group. So let's first go to the table and find a methylene attached to a benzene ring. All right, that would be right here. The ranges were given 2.5 to 2.9, and take the average 2.7. So the contribution of the benzene ring, the effect on chemical shift of methylene, would be an estimated 2.7. And back to the molecule again. We want to now go to the table to see if we can find an ester carbonyl group attached to the methylene. All right. And we look and we're not it's not there. We're not find that exactly, so we'll estimate. We do have a methylene attached to a ketone carbonyl group. So that's as close as we can come, and since we're just doing estimates and not going to get exact agreement, we'll use the values here as an estimate. And the average between 2.3 and 2.7, 2.5. So the effect of the carbonyl group on the methylene will estimate a chemical shift of 2.5. Now we've got those two estimates, 2.7, 2.5. Here's one thing that we can do to get a better estimate. When you have a carbon-bound hydrogen attached to two substituents, two groups, find the chemical shift value from the tables for each substituent. We've got the phenyl group and we got the ester carbonyl group. Of course, we didn't find the ester carbonyl group, we had the ketone carbonyl group. Now these are the two values I found in the table. Methylene attached to a benzene ring has an estimated chemical shift of 2.7. Methylene attached to a carbonyl group from our table is 2.5. We got these two values. Now, what we don't want to do, which might seem logical, is to add them together to make our estimate. A better approach is to do this. Take those two values, one value for each substituent, and take the smaller of the two. All right? Take the smaller of the two and divide it by 2. Take the larger of the two as our starting value and add to it the value that's half the value of that we got from the table. That is, add to it the value from the table divided by 2, which in this case would be 1.25. And you add these two values together. The value for one substituent, the value for the other divided by 2, 2.7, 1.25 gives us 3.95 as our estimate. All right, we'll go back now to the spectrum. So we're going to estimate 3.95, and oh goodness, you know, the other estimate we had was I think about it was 3.9. This is 3.95. They're too close together to really be able to decide which of these signals corresponds to which methylene. But what's going to give us our answer here is the splitting pattern. And let's now analyze the splitting pattern in this molecule. Let's return to the methyl here and decide how many peaks there will be in its multiplet. To do that, we use the n+1 rule. This methyl group is attached to methylene. These two methylene hydrogens are neighboring hydrogens to the methyl. These two methylene hydrogens comprise a set of two equivalent neighboring protons with respect to the methyl signal proton. All right, so how many peaks, how many peaklets are going to occur in the methyl's multiplet? Well, use the n+1 rule. N here is the number of equivalent neighboring protons, which would be 2. We add 1 to that, and we get 3. 2 plus 1 is 3. Indeed, we predict a triplet, and we see the triplet here. And that confirms our assessment that this signal is due to this methyl. All right. Now, what about the other methylene here? What about its expected splitting? It's attached to a carbonyl carbon, attached to a benzene ring carbon. We'll notice that there are no neighboring protons. There's no hydrogens attached to that carbon, and there's no hydrogens attached to that. So there are no neighboring protons. So this CH2 is unsplit. It's just a singlet. And indeed, when we were examining these two, it's this. That's the singlet, and therefore we ascribe this unsplit singlet to this methylene. That's our assignment, that this methylene here is associated then with this signal. And now we come to this methylene. What do we expect for its splitting? Now it's the signal proton, the signal set of protons. How many neighbors does it have? How many equivalent neighboring protons does it have? Well, it's attached to a methyl group. These methyl hydrogens are neighboring protons with respect to that signal methylene. There are 3 of these that are equivalent, a set of 3 equivalent neighboring protons. Therefore, the value of N is 3. We add 1 to that. 3 plus 1 is 4. So the number of predicted peaks in the methylene's multiplet would be 4. And indeed, here it is. This quartet here would correspond to indeed that methylene. The signal at 7.2 delta is associated with the benzene ring hydrogens. The signal appears to be a singlet, but strictly speaking, it is not, because as you can see, there is some broadness at the base of the signal. It is not a sharp singlet because the ring hydrogens are not equivalent. They consist of ortho, meta, and para hydrogens, which are in different environments. So there's the complete analysis, interpretation of this Nmr spectrum for ethyl phenyl acetate. All right, I want to return to the topic of spin-spin splitting. I want to address 2 questions. First of all, how close do protons in a molecule have to be considered neighboring protons? And secondly, what's the general magnitude of the splitting that we see for proton-proton couplings? And by that I mean, when we have a multiplet, what is the magnitude of the spacing between adjacent peaks in a multiplet? To answer those questions, let's go to a different table, this. This table does 2 things. It lists structural types where we find protons that would be considered neighboring protons. And it also lists the magnitude of the splitting between those neighboring protons. All right. Now let's look at this entry, these 2 entries. The hydrogens that are colored, respectively red and purple, are true neighboring protons. There's going to be splitting between them, causing multiplets in an Nmr spectrum. We have the situation here that we'd have actually seen before, where we have hydrogens bonded to adjacent carbons. The magnitude of the splitting that we normally see is, well, for this situation, 6 to 8 hertz, and for this 5 to 7 hertz. Let me mention in this regard is that In measuring the magnitude of splitting, the spacing between adjacent peaklets, we don't use ppm. Instead, we use frequency hertz, and that turns out to be the better unit to use. Alright, let's look at some other situations where we have some other structural types where we have splitting. Now here's a situation where we have hydrogens bonded to adjacent carbons, but the issue here is the so-called dihedral angle between the two CH bonds. That has an effect on the magnitude of the splitting. And that situation arises when we have hydrogens, let's say, on a cyclopentane or cyclohexane ring. And that actually can vary over a fairly wide range. So the value of the angle has a big effect on the actual observed magnitude of the splitting. It can fall in the range 2 to 12. Now here's an interesting situation. We have two adjacent carbons, hydrogens on each, but one of the carbons is a carbonyl group. The magnitude of the splitting is actually smaller than we saw before, say 0.5 to 3. Now look at this structure. Here we have two hydrogens on the same carbon. Notice these hydrogens here are even closer than they were when they were attached to adjacent carbons. Being so close, this is going to lead to a much larger splitting magnitude. The magnitude on average is from 12 to 15 hertz. That's larger than what we saw before, say 5 to 7. Now, hydrogens, if they're going to split each other, if they're going to be neighboring hydrogens and split, they have to be not equivalent. We've seen situations where we have two hydrogens on a carbon, a methylene set, that are equivalent, and equivalent protons do not split each other. Well, what situation would we have that would give rise to this, where we have two non-equivalent hydrogens on the same carbon, bonded to the same carbon? The answer would be in a ring-type structure. We can look at examples of that later on. All right, moving to the right half of the table. Structure type here is where we have protons bonded to a carbon-carbon double bond. Three situations. The hydrogens are trans to each other. They're on different alkene carbons where they're trans, where they're on different alkene carbons and cis, and where they're attached to the same alkene carbon. Interestingly, when the hydrogens are trans, the magnitude of splitting is actually larger, 12 to 18 hertz. When they're cis, 7 to 12. Now, ironically, when they're both attached to the same alkene carbon, you might expect, since they're closer together, you might expect them to exert a larger magnitude of splitting, but that's not the case. It's actually smaller. So that these two neighboring hydrogens here have a smaller splitting effect, a magnitude of 0.5 to 3 hertz. Here's a situation where we have a proton on a carbon attached to a alkene group, namely these two hydrogens. And in this situation, it also depends on the so-called dihedral angle, the angle between the CH bonds. And there's a wide range depending on the angle, from 3 to 11. In this structure type, we have a aliphatic proton and a carbon bonded to a CC triple bond. The hydrogen questions are the acetylenic hydrogen and the nearby aliphatic hydrogen. There is an expected splitting of 2 to 3 hertz. When you have ring hydrogens, what you generally find is that the closer the neighboring hydrogens are, then the larger the splitting effect. If they're ortho, it's 6 to 9, meta 1 to 3, para 0 to 1. Now, one thing I didn't mention is there's a general term that we use for the magnitude of the splitting. It's called the coupling constant, and it's given a kind of standard symbol, capital J. J is the standard symbol for coupling constant, the magnitude of the splitting.